Hello and welcome to our talk. My name is Michael Lay. I work at IBM Research, and my co-speaker today is Sascha Grunert from Red Hat. We'll be talking about our talk entitled "Don't Trust Your Neighbors: Securing Pods via Scheduling." This work was done in collaboration with other folks at IBM: Salman Ahmed, Daniel Williams, and Hani Jamjoon. So here's a diagram that shows a typical uh, deployment of a Kubernetes cluster. And you have your typical set of nodes. On each node run a set of pods, and inside the pods there can be one or multiple containers running. The containers on the pods all share a single highly privileged kernel, and the containers typically deploy some applications that can have a very wide, diverse system called usage profile. Um, and within the containers, there could also be some deployment of system called filters, like seccomp filters, being used to enforce security for that pod. Um, in a typical deployment, whether it's a multi-tenant cluster or a single tenant that have, using namespacing for isolating different usage, users typically do not have very fine-grained control over who are the neighboring pods on that node. So some of these pods might have access to some system calls that can be quote unquote risky. And these pods using these risky system calls can exist on the same node with other pods. Yeah, so what do we mean by risky system calls here, right? So in some sense, these risky system calls could be system calls that have been known to have some vulnerabilities in them that might be used for or known to be used in, existing exploits before, or just system calls that in general rarely used that potentially could be, have potentially have bugs and vulnerabilities in them. Um, so the fact that these pods have access to some of these potentially risky system calls, we dubbed those pods as bad neighbors, bad in relative to the other pods on the system who don't use these risky system calls and have to be next to these pods that do use these system calls. And because the fact that they all share a single privileged kernel, that means these containers that have access to these risky system calls can potentially exploit those vulnerabilities, do some kind of privilege escalation, and take over the kernel. And if that's the case, can break out of containment, and now you have ability to jeopardize the other pods running on the same node. And these other pods are what we call some of these victim pods and victim nodes, so to speak. So the question then is, yeah, given this problem, uh, is there a way to improve the situation? Can we improve security by effectively reducing or avoiding the impact of these bad neighbors? So what we observe is that if you have a cluster and you have some, um, pods that are quote unquote bad neighbors, um, you could potentially use scheduling if you know in advance some information about those pods and why they're bad. You can use that information before you do placement and effectively group them all together into one node or set of nodes, and isolate them from the rest of the system, the rest of the good pods. And this is effectively the underpinning kind of mechanism that we try to design and implement and evaluate, and sort of thrust the main focus of this talk to discuss with you how we go about exactly doing this. Okay, so in the remaining part of the talk, we will go deeper into what Sysched is, how it works, and the security benefits that can be had. Um, After that, Sascha will discuss in more detail how Syscall is operationalized, mainly the security profile operator, and how we use that to get access to these pertinent information about the pods in order to do the scheduling. After that, we will have a little demo showing how Syscall is deployed in a Kubernetes cluster, mainly as part of the scheduling pod, as well as how SPO is deployed and how we leverage SPO to get the information needed for scheduling. After that, I will quickly discuss about some evaluation we've done, showing the benefits for in terms of security as well as any kind of performance impact that can be seen from this work. So underpinning Sysched is this metric that we've defined called extraneous system calls, or XS. This metric effectively defines for a given pod the number of system calls that that pod does not need or does not use, but however, that it is being exposed to by the fact that the other pods on that node, its neighbors, are using. So these are extraneous system calls with respect to that target pod, that pod in question. So this sort of captures, for a given pod, the amount of risk it has when it's being deployed on a particular node, given the set of pod that already existing on there. So as you can see from this diagram on the right here, it shows a node that has three pods, P1, P2, and P3, and these numbers on the bottom, 1, 2, 3, 4, 5, 6, 7, 8, 9, are just representative of system calls. So for a pod P1, you see the top figure there. It has system calls 1, 2, 3, and 5. And for this particular pod, the XS set of system calls that are extraneous to P1 would be 4, 7, 8, and 9, since these are the system calls that are used by other pods on that node that the pod P1 does not use. So the XS score here would be 4. And you can see from P2 and P3 it follows from that description. So at a high level, Sysched for any incoming pod, Sysched calculates this XS score for each pod against each pod and every feasible node in the cluster, and then it uses this score to rank the feasible nodes and selects the node with the lowest XS score, meaning that node has the lowest risk for that particular pod that's being scheduled. So before we go any further, it's actually important to step back and take a look at what are the reasons why we think this particular scheme would work out. And it has to do with the fact that if you were to look at all the pods that are running workloads out there, if they all effectively use the same amount of system calls, the exact set, or they use all the system calls that are available, then there's actually no room to really differentiate uh, one pod's use of system calls from another. So the XS score, the extraneous system call would effectively be 0, and there would be no discrimination between placing a pod on one node or another. So we took a look at about 45 popular containerized applications from Docker Hub, and we did a system called trace using dynamic tracing, running a representative workload on there, and we discovered that uh, there's a small amount of system calls that are used by all of these applications. So typically, we found out that between 9% of the system calls on a Linux system, which is roughly about 335 system calls, about 9% of those system calls were used by some application, and it could go all the way up to about 37% of those 335 system calls were used. So as you can see, there's a sort of a large variation of number of system calls that are being used by actual application, and certainly it's not the case that all the system calls are being used, or even a very large fraction of being used. So this range gives us hope that there is room for scheduling and using this XS score and be able to use that score to discriminate between placing a pod on one node versus another. Another indication where this Sysched approach would work well is that there's also a very large variation in the similar system calls that are being used across the different applications. So we found out that there's as little as 23% that are similar between any two applications, and as large as 99% that are similar. So this tells us that there's a large room to play here, being allowing us to actually use excess score to do the discrimination and do the ranking of the placement decision for each of the incoming pod for a given set of nodes in a cluster. So this slide presents a scheduling example to show in detail how SySched scheduling algorithm actually works. So this is a example of a cluster of just two nodes. So in column A, you see the nodes are initially empty, and the pod 1, P1 is an incoming pod to the cluster, and it has a system called 1, 2, 3, and 5. Sysched calculates the excess score, which in this case is 0 for both nodes since there are no other pods, no other neighbors potentially. No other neighbors on those nodes. So Sysched will have to randomly pick a node to place P1. So it picks node 1 to place P1, as you can see in column B. So in this column, there's also a second pod, P2, that's coming in, and Sysched calculates the excess score for P2 with respect to different nodes on the system. So in this case, Sysched calculates excess score of 7 for node 1, and the excess score of 0 for node 2, since there's no pods running on node 2 as of yet. So given these two scores, Sysched will have to pick the smaller excess score to place P2, which is in this case node 2. So in column C, you can see the placement of P1 and P2 on the respective two nodes. And then there's an incoming pod P3. Sysched again calculates excess score for P3 given the existing pods on those candidate nodes. In this case, for node 1, excess score is 2, and node 2, excess score is 7. And picking the lowest excess score for node 1, Sysched places P3 on node 1. So this is effectively the how overall Sysched performs its scheduling and placement decision.
So Syscall also supports the use of weights for different system calls. So the weights can denote or indicate the riskiness of certain system calls or a group of system calls. And weights gets added to the excess score, depending on the system calls that the weights are associated with, and it can make the presence of a pod using such risky system calls be less attractive as a neighbor. So for instance, if you have some system calls, let's say, that are rarely used, uh, um, you can add a weight to that system call. And if there's a pod that happens to use that system call, that pod will effectively be shunned by all the incoming pods that are into that cluster. So the weights can have different values. It can be -1, meaning that particular system call, if it's found, used by any pod on that node, it would be not considered as extraneous. 0 indicate that it is extraneous, but there's no special consideration, but other than the fact that it is extraneous. And if any number greater than 0 would mean that it's extraneous, but it's also a large number. It can be a large number, and that number, the magnitude of that number, indicates effectively the amount of risk that particular system call has to the system. So, the administrator can transform the notion of risk into weight values. Some examples of where risk can come from. It could be derived from, for example, from a CVSS score associated with some CVEs that are known to impact the kernel and maybe have some associated system calls with those CVEs, including other techniques that have looked at the type of system calls that are used in the wild and in exploits, and look at how those system calls are being used and whether those system calls are unique to those exploits. And given that information, that analysis, you can then transform those risks to some weights that then can be applied to Sysched.
So now that we understand what Sysched in general does and some of its basic mechanism, it's a good time to kind of step back a little bit and talk about what Sysched does and does not do. So to be clear, this solution that we are talking about today does not prevent the use of risky system calls or system calls that are potentially vulnerable um, from being executed in a pod. So it doesn't prevent that at all. And it definitely does not prevent an attack leveraging system calls, such system calls from being used and exploited. So an attack can still happen. It doesn't prevent an attack. However, what it does do, hopefully you can see from the example in the previous slide, is that it tries to collocate, group together potentially harmful uh, pods that use these system calls, centralize them in a way and remove potentially pods that don't make use of those system calls, and try and isolate them away from these potentially riskier pods. In this way, what it does do is, on average, what it reduces effectively the blast radius of an attack. So if an attack were to happen and succeed, it limits the number of nodes that the victim nodes that occur. Comparing to some kind of default scheduling where that those malicious pods could be spread out evenly across the nodes in the cluster. It instead clustered them together in some central area. And then in addition to that, it reduces the number of victim pods that the attacker might have access to. So those are the main things that Sysched does not do, and the things that it does do. In addition to that, in the way that because we use system calls as a way to do scheduling, um, the idea is that if a developer who wants to develop some software for a container, this person could be more cognizant of which system calls to use and not use, and be careful about the number of system calls that could be associated with certain libraries he or she uses in order to reduce the amount of system calls that are unnecessary, and be a good citizen effectively in this ecosystem. And by doing so, we hope to have a way to incentivize the usage of safe system calls and the number of limited system calls that are necessary in a pod. In this way, we could hopefully have a much more secure and more cognizant approach to developing software in the cloud. So this slide here shows the overview of how Sysched is designed and how it fits into the overall Kubernetes scheduling framework. So in pink here it shows the Sysched component. So Sysched can effectively be run as part of the main scheduler, as part of a single scheduler in the system, or it can be run as an independent secondary scheduler in its own pod, depending how you configure your scheduler. And for this diagram, you can see that when pod comes in, the scheduler works by first applying a set of filters to this pod. And if the set of filters can, be, for example, one of them can be identify all the nodes that have the appropriate resources to run that pod. Once this feasible set of nodes is determined, it gets passed to a set of algorithms to rank the feasible nodes and select the best one. So effectively, these algorithms are these scoring plugins, and Sysched is one of these plugins that gets applied to rank the feasible nodes. And Sysched, so you can configure the scheduler to run, a set of these scoring algorithms or a set of these filters, or you can select, from one to many different combinations as you want. You can run Sysched also by itself to just primarily use the Sysched ranking algorithm by itself and independent of anything else, or you can combine it with other mechanisms that are already there in the system, depending how you want to configure your scheduler. So Sysched in general is pretty easy to use and deploy. However, one of the main challenge of using something like Sysched is its reliance on being able to generate the system call profile for the pod. Even though this is an orthogonal problem to our scheduling mechanism that we discussed, we nevertheless use system call profiles to kind of inform our decision of how to do scheduling. So uh, getting this profile is effectively, essentially very important for us, and how to do so easily can facilitate using this mechanism of scheduling that we propose. So um, the there are several ways to generate the system call profile for a pod. You can go from a static analysis way. There's a lot of good work around that. You can also go, you also can have assume that the system call profile is supplied to you by the developer. Giving you, here's a application, here's a pod, and here's a set of system calls that generated for you. That's probably less likely that that will happen. So in most cases in industry, a dynamic approach is often used where the pod is is run and then run for some time while the pod is being exercised, and the system call set that's being executed is recorded, and that becomes your system call profile. So fortunately for us, there is a great open source project called Security Profile Operator that goes about automating and managing a pod's system call profile and its SecCom profile on a pod's behalf. And we leverage that very greatly, and we have a very close integration with that mechanism in order to allow us to use Sysched in a very comfortable and easy way. So we'll discuss that next, and Sascha, my co-speaker, is going to be introduced the Security Profile Operator (SPO). Please take it away, Sascha.
Thank you, Michael. So the security profiles operator is a Kubernetes operator for managing security profiles as custom resources. So it supports SecCom profiles, AppArmor, as well as SE Linux. Its main purpose was to synchronize profiles across worker nodes automatically so that the user don't have to take care of that manually, which is the case if they don't use something like the security profiles operator. This means that the user usually just deploys the operator, which is a manager, and this manager takes care of updating and creating a daemon set which runs on every node or on every configured and selected node. And this daemon set uses an internal daemon which watches and updates and is also capable of creating those SecCom profile, SE Linux profile, and AppArmor profile custom resources. Users can now directly interact with those profiles, like modifying them, creating new ones, or also deleting them. And the daemon will take care of watching all pods which actually use those profiles, will install them on the node before they actually can use them. And if the usage of the profile is gone, then the daemon will also take care of cleaning up those profiles and removing them. The whole layout of the profiles on disk is specified by the security profiles operator, and the custom resource will help users to actually use them in an easier way and also to split responsibilities between system administrators and cluster users, which are just the consumers of those profiles. And this is how the security profiles operator provides those custom resources as an example of SecCom profiles. So usually we can define SecCom profiles as an allow list for Syscalls, which means that we just have to provide a kind SecCom profile, then we just give it a name or provide additional metadata around it. And the default action is a SecCom action error no, which means that the syscall gets blocked. There are a couple of other actions available, for example, just allowing syscalls or logging them to audit log, or also tracing them or killing only the thread and things like that. But error no is one of the most common ones. We also have to define the architectures for which our SecCom profile should apply. So different kernel architectures can also provide different environments where different syscalls are available or not. This also depends on the kernel version, for example. And then we specify a list of syscalls which are actually allowed in our container. In this case, we provide a base profile for run C, which allows a couple of syscalls. Not all of them are displayed here, but for example, we cap get, cap set, and change here are some syscalls which are required by the OCR runtime run C to actually start a container. But security profiles operator has a way more extended feature set other than just providing those custom resources and syncing them on disk. For example, we have different configuration options in the security profiles operator. We are able to bind profiles to actual workloads. We can also stack profiles, as we already saw in the run C base profile. So this can be stacked on top of a different SecCom profile so that you just combine the allow list. We also have a lot of metrics and a few experimental features, for example, like enhancing edge cases and stuff like that. One of the main features is the profile recording, which can be done by using audit log parsing or eBPF. And if we now look at the architecture of the security profiles operator when we speak about eBPF-based recording, then things get a little bit more complex, right? So we don't have just a manager and a daemon set. We also have a webhook, which adds annotations to pods, and the daemon will watch those annotations on the pods and will then tell the eBPF recorder to record Syscalls. So starting and stopping recorder will be done by the daemon and a dedicated eBPF recorder instance on the node. The eBPF recorder then records the profiles, and if it's done, then the daemon tells to stop the recording again, and then the daemon will take care of installing the profile. So how will an end user actually use the feature? End users have to use a different custom resource for that. So the profile recording custom resource can be created by end users, and then the daemon will also watch those resources and will act based on that. Let me give you a demo about the profile recording in the security profiles operator. Well, first of all, we have to double check if everything is up and running. So the security profiles operator relies on Cert Manager, for example, if we deploy it on plain Kubernetes. And then we can see that the SPO is running and the webhook is running as well. And we also have our daemon, which is called SPOD. And this is also running and configured that a BPF recorder is enabled. To actually be able to record something, we would like to label our namespace, which is the default namespace with enable recording. Otherwise, the security profiles operator will not do anything at all on this namespace. And if we now look at our example recording, then we can see that we want to record a seccom profile is using the eBPF recorder, and that we have a pod selector which matches App Nginx. So we now can apply this recording to our cluster, and then we can double check if the recording is available. So we can get profile recordings, and then we see, okay, our recording with the match label app equals Nginx is available in the cluster. If we now would like to run an example pod, which can be an Nginx server, for example, then we can see, okay, this is a usual pod, which has the label app equals Nginx. And if we apply this pod, and if it's up and running, then we can just query the Nginx URL to see if it's working. Yeah, we have our main landing page for Nginx. And if we then delete the pod again, which should now produce some Syscalls, then we can double check if we have a seccom profile available in our cluster. All right, so we have the recording container seccom profile, which got installed 7 seconds ago, and it's available in this localhost profile. And if we now look into the seccom profile, then we can see that it contains all the syscalls required to run the Nginx profile. And for example, we have to bind an address, we have to allow connections to be coming in, and this profile is now ready to be used from our pod. This means if we now change the pod manifest to actually contain the localhost profile about our current recording, and then apply this pod, then the pod should be up and running again and use the seccom profile now. And if we now use curl again, then we run our pod in a more secure environment, but it all still works as intended. So there are a bunch of interesting insights when you speak about eBPF-based seccom profile recording in the security profiles operator. We use, for example, CORE, which means compile once, run everywhere, to achieve maximum portability of code. We also use the mount namespace for tracking processes because it can be possible that we have multiple pits inside of a single container. We also did some reliability and performance optimizations to be able to to record multiple containers in parallel, and also, for example, to cache the process and how namespace relation, and also the container lookup, which will be done by zgroups by us. We also support now merging recordings by using replicas. So if you use a deployment and then record the deployment, and then use, for example, a service to actually access the pod, then the security profiles operator is also capable of merging the recordings together into one. So all in all, eBPF is one of the most reliable ways to record syscalls, but it comes with a bunch of downsides. So there is a security concern because eBPF programs run kernel scoped, so they see all processes running on a single node. And those syscalls can also differ across different kernel versions and architectures. So on some architectures, some syscalls are not available at all, and also some kernel versions don't support all syscalls, so there can be some backup paths when recording those profiles. This means that depending on how your configuration in your Kubernetes system is set up, also OCI runtimes use different syscalls to set up the containers. So in the end, when you record profiles, you should ensure that you have an as close as possible test environment to the production environment. There are a bunch of great recent enhancements to the security profiles operator. For example, we were working hard on productizing the SPO. And for example, we have Helm chart deployments, our usual customized based deployment, and we also support Operator Hub. So this means that we now ship it in OpenShift as well. And we are also working on optimizing the SPO for edge scenarios. So we provide now a command line binary, which works even without Kubernetes at all, and which supports recordings and replaying SecCom profiles, as well as storing those profiles as OCI artifacts and registries. We were also evaluating extended SecCom profiles, so we can categorize syscalls if they're risky or slow in different categories, and then we group them together, and we make SecCom profiles a higher level abstraction. If you want to learn more about the security profiles operator, just scan the QR code or reach out to us via Slack.
Okay, great. Thank you, Sasha, for that. And now to show the end-to-end picture of how SPO is integrated into SySched. The slide shows the first step of the first order of business is to collect the system call profiles from a pod. And you can see here from this diagram, the pod can be run in a dedicated cluster, specializing in running these pods that have not been seen in the cluster before, or maybe a subset of nodes inside an existing cluster. The idea is to just run the pod application for a while and collect its system call information, and then upload that to the SPO. And once that is done, the SPO, these CRDs that belongs to the SPO can be bound to the pods, so that when the pods are created, they can have access to these CRDs in the SPO. And once that is done, Sysched can then now be used as a way to graduate these pods that are run beforehand in these dedicated isolated cluster into a more hardened and more trusted area of the cluster for production, perhaps. And Sysched can then uses the pod CRD information for SPO to then do its placement. So we have a little demo here to kind of demonstrate and show how the scheduler plugin is deployed, as well as how to deploy the SPO and create the system call profile CRDs and bind those CRDs to the pod so that when the pods are created, it will be able to access the CRDs that the SPO provides containing the system call profiles. In addition to that, we'll also show how the pods are deployed onto the default scheduler and using the Sysched scheduler, and be able to show the placement differences between the two, given the set of pods that we use and the associated system call profiles. So towards that end, the slide here captures the scenario that we will be showing off in the demo. They're the two identical scenarios, just one set of pods being deployed by the default scheduler and the other set of the same set of pods deployed using the Sysked. And the set of pods here contains two Redis servers, a ProFTP, a Memcached, MongoDB, and Nginx. The two pods in red, ProFTPD1 and MongoDB1, These are marked in red because in this scenario, they don't have a seccomp profile, so they are unconfined, meaning they have potential access to all system calls available in the system. And in our sort of application, with respect to Sysched's point of view, this is sort of the worst neighbors you can be next to because they have effective access to all system calls that potentially can be dangerous or have vulnerabilities in them. And so you'll see that in the top scenario, using the default scheduler, these two pods will be placed, randomly in this example instance as we create for you. They will be placed in node 1 and node 2, whereas in the second demonstration where we're using Sysched, because Sysched looks at the different system call profiles being used, you see that they will end up clustering together onto a single node, running, on a single node, so that any kind of fallout from an attack will be contained to that node rather than spread across different nodes as in the first top example. Okay, so now I'm going to run the demo, and in this demo, we will first build the local system call Sysched plugin that we will then deploy as a secondary scheduler. So you see it just being built. That's just a common process. Once it's being built, we push it into our local repository. And after that, what we do is we have to do a little modification in the manifest of the scheduler, make sure it points to our image, as well as both the controller as the scheduler, and then add the Sysched as part of the configuration file, the plugin that's being used. And then we effectively use the Helm chart to deploy it. Pretty simple. You can see there both the scheduler plugins controller as well as the plugin component is being run right now. Okay, so the next step here is to install the security profile operator, the SPO. This is also a straightforward manner. First deploying a cert manager to get all the access control correctly defined. And then we effectively just use the script available in SPO's repo to deploy the different components. Yeah, so see from the pods what's being deployed. You see there's a few pods there, and security profile operators there that are running. And so now you have security profiles running as part of the cluster. All right, so the next step here is to install the different system call and create and install the different system call profiles, the CRDs that are used by SPO. So in this step, we assume that the recording of the system calls have been done, and they are already recorded, and they are in this file. These different files you see for Nginx and Redis, as well as for memcached, and these example that we're showing here. And then we're just applying these YAML files, and after they're applied, the CRDs are effectively created in SPO, and you can see them once we list them here. So now we create the profile bindings, binding the SPO CRDs to any pods that will get created. Yep, so you can see here all the profiles have been bounded. All right, so next thing now is to deploy the 6 pods that I mentioned earlier, and deploy them using the default scheduler. And you see at the end of deployment, its layout, its configuration. So I mentioned before there's two red pods, both Mongo and ProFTP. They're in two different nodes, right? Node 3, node 2. They're spread out, even though they are potentially the most risky, have the most risky system call profiles given their nature of accessing all system calls because of they being unconfined. In the next case here, we deployed the same set of pods using Sysched, and you can see the layout that will be shown here, that these two pods, MongoDB and ProFTP1, are located in node 2. So they're kind of co-located together and contained. Okay, that's the end of our demo. So now you've seen the demo. I want to just briefly talk about the evaluation that we've done in terms of looking at the security benefits as well as some potential performance drawbacks and overheads. This is only a brief overview, giving you some notion of the benefits you can have and potentially some overhead that you should consider. A lot of the details I can discuss later when I reference the paper that we've written on this topic, so you can find more details there. So in order to run this evaluation, we selected 42 unique applications that are known to have a high volume of downloads from Docker Hub. These applications span effectively 11 different classes application types, from FTP servers to web servers to databases to various different types of applications. The cluster, we have set up a cluster that can grow up to 42 nodes and can have 126 pods are used for scheduling. So each of the 42 application can have up to 3 instances that it runs on this cluster. So, there are two questions we want to answer. First, what are the security benefits, and if there are any? So with that regards, we looked at two questions. First, is there a reduction in the overall excess number, right, the score? Remember, SX measures the number of extraneous system calls that are seen by a particular pod that's being scheduled on the system. And we compare this to a default vanilla Kubernetes scheduler where it just does the scheduling based on placing the pods on the next available feasible node. And we've shown that there can be actually up to 2 times better when Sysched is used in reducing this excess score. So that's great news, right? There's a lot of room for opportunities for improvements there in terms of limiting the number of extraneous, potentially bad neighbors you have. The second thing we looked at was that, lowering the excess score is great, but does that actually translate to actually any concrete security benefit, this reduction of blast radius that I mentioned earlier. So what we found is that when we looked at, we assume certain system calls have associated CVEs with them by looking at the historical set of CVEs that are out there over the past about, I think, a decade. We have shown that with Sysched compared to the default scheduler, we can reduce up to 46% and 48% respectively of the number of victim nodes and pods for a set of these 50 CVEs. So, we've shown that, with very minimum amount of work you have to do, you can actually get some pretty decent security benefits by leveraging information that is already there, known to a running pod. So that's great. Now, looking at the performance, one critical aspect of this work is that, you can observe that, when pods are similar in characteristic, they tend to be scheduled together. And that could translate to potentially having similar application types, let's say like database or web servers, get scheduled onto the same node. And does this present a kind of performance overhead, performance risk? And the answer is, maybe not too surprisingly, that it really depends. In some situation, it can be, if that node is, constrained on the resource that's being shared by these different pods that use the same type of application. So in that case, for sure, there's going to be some penalty. However, if the node has room for these applications to run on, even though they share the same resources, the performance impact is actually negligible compared to a similar distribution of these pods on a different set of nodes rather running the same node. So it's all a matter of the sizing of the resources that are available on that node to running these similar applications. So it's not always the case that by default, the fact that you run this application the similar application on the same node, you get worse performance. It really depends on the nature of the resources constraint on that particular node. So the current status of our work is that SySched right now is we're open sourcing SySched, and we've got SySched open sourcing into the Kubernetes SIG scheduler plugins community, and we've got the KEP accepted already, and we're working on finishing up the PR. We've already sent in the PR, but we're working with the community trying to get it accepted. Modifying the code is necessary to do so. Some to-dos that are going on, and a couple of interesting things. One is handling Syscalls being able to handle different type of SecComp policies. Like besides allow, there could be some disallows, or it could have some kind of just purely log, or having no SecComp profiles at all. So we have ways to handle some of those, but not cleanly yet and not thoroughly. So we work through to kind of manage some of that. We also want to consider about extending some of the SPO mechanism and somehow some of the information in the CRDs to encode some risk information in system call profiles, right? So, whether system calls can be risky, have some weights, that information can be not only used for us, but potentially others who make use of this information to do some other type of scheduling or to other type of security products. In addition to that, the last thing is that we want to account for pod information that are the runtime information